Okay, today we move on to 6C, which is on orthogonal complements and minimization problems. Okay, so as always, V is going to be an inner product space. Right. This is true basically all through this chapter and the next. Okay, so today we're going to talk about orthogonal complements. And an orthogonal complement of a subset, not even just a subspace, but of a subset, is just all of the vectors that are orthogonal to that subset. Definition. So if U is a subset of V, then the orthogonal complement of U which is denoted U perp, so it's a little perpendicular symbol, perp, is the set of all vectors in V that are orthogonal to every vector in U. It's horrible. In other words, U perp is just defined to be all the vectors in V such that the inner product of V and U is 0 for every U and U. Okay, all the vectors that are orthogonal to some subset. Okay, so we have some examples, of course. So in R2, you can take U to be, say, this subspace, this line to the origin, and then all the vectors that are orthogonal to every vector in U is this subspace here. This is the normal inner product. This is U perp. Okay, in fact, you can let U just be the single vector, like this single vector, if you want. I guess the way I've drawn it looks like 1, 1. I can let U be just the vector 1, 1. And this red line is still the orthogonal complement of that set. Or I could let U be the whole subspace. Maybe I should call this like U prime. Right, so U prime perp is also equal to U perp. The point I'm trying to make here is just that you can define the orthogonal complement of any subset. It doesn't need to be a subspace. So you could take the whole subspace U and take its orthogonal complement, or you could take the orthogonal complement of a single vector, which is not a subspace, but you can still define the orthogonal complement. Okay, and then like in R3, again, let's say you take a single vector and you let this single vector be the entire set U, or you could take the entire line to the origin. It actually doesn't matter. Maybe I'll just draw this entire line to the origin. Then the orthogonal complement will just be the plane whose normal vector is that vector. This is U perp, the plane through the origin. Okay, so at least in Rn, you can picture things geometrically, and it gives you some idea of what to expect out of orthogonal complements. They should behave something like these pictures do in Rn. But of course, we'll need to sort of prove any property, right? But like, just from these pictures, some things that you could maybe hope is true for orthogonal complements. For example, it seems like the orthogonal complement of U perp might be U. So if I consider this whole plane and I ask, what are all the vectors that are orthogonal to every vector in the plane? It seems like all I'm going to get are the vectors in this line. So maybe if you take a subspace and you take the orthogonal complement twice, you get back to where you started. Also, it seems like maybe there's some sort of dimension thing happening. Like this is R3, it's 3-dimensional. If you take U to be the subspace, then U would be 1-dimensional and U perp is 2-dimensional. So maybe the dimensions add up. Right, so these kinds of things, we can get some intuition from thinking about the Rn geometric picture course, anything that we want to know, we'll have to prove in abstract. Okay, so basic properties first. Here are the properties. So one, if U is just a subset, V, then its orthogonal complement is always a subspace. Okay. Two, the orthogonal complement of the zero subspace is all of V. Three, the orthogonal complement of V is the zero subspace. Four, if U is any subset of V, then the intersection of U with its orthogonal complement is just the zero vector. Again, this we can kind of see from our picture that we might expect this, right? If you look at a subset or subspace and its orthogonal complement, at least in these pictures, they only share one vector in common. And then the fifth one is if U and W are subsets, and U is a subset of W, then the perps, the orthogonal complements, share the opposite inclusion. In other words, the bigger the subspace you take, the smaller the orthogonal complement you'll get. Okay, so these are basic properties, which means we should be able to prove them just using the definition. Okay, so one, I need to show that the orthogonal complement of any subset, again, I'm not requiring U to be a subspace, just a subset. I need to show that it's a subspace, which means I need to show that U perp contains zero and is closed under addition and closed under scalar multiplication. So first note that zero, if you take the inner product of zero with U, this is zero for every U and U. This is by properties of inner products that we proved. I mean, in fact, this is true for every vector V and V, right? But it's definitely true for every U and U. And this is just the definition of what it means to say that zero is in the orthogonal complement of U. It's orthogonal to every vector in U. Okay, now suppose that V and W are both in U perp. I need to show that U perp is closed under addition, so I need to show that V plus W is in U perp. Right, well, to say that V and W are in U perp just means that if you take the inner product with U, you get zero. Which will mean if you take the inner product of V plus W with U and use linearity, that this is equal to zero. Linearity in the first slot. So the inner product of V plus W with U is zero. That means that V plus W is in U perp. So it's closed under addition. And then sort of as always, I'll let you handle closed under scalar multiplication. Check. It should be like a one-liner. Okay, so if you do that, then that proves part one. Okay, part two and part three are just essentially just definition and the fact that the inner product with zero is always zero. Right, so for every V and V, the inner product of zero and V is zero. This is by, again, properties of inner product that we showed last time. But this means that every V and V is orthogonal to every vector in the zero subspace. Right, so in other words, for every V and V, V is in the orthogonal complement of zero because it's every vector is orthogonal to every vector in there. And so this means that the orthogonal complement of zero is all of V because every vector in V is in there. Three. I want to show that the orthogonal complement of the whole space is the zero subspace. So suppose that W is in V perp. What does this mean? This means that W is orthogonal to every vector in V, every vector. Which means that also W is orthogonal to W, right? Because V perp is a subspace of V. That means that W is in V. Then also W is in V. And since W is in V perp, it's orthogonal to every vector in V. That means it's also orthogonal to W. But we already saw that the only vector that has this property is the zero vector. This is by definiteness of the inner product. Right, so the only vector in the perp of V is zero itself. Okay, and actually this same exact line of reasoning is what proves 4. If U is in U intersect U perp, then that means that this means that U is in U and U is in U perp. And since U is in U perp, it means that it's orthogonal to every vector in U. In particular, it's orthogonal to itself. So the only thing in the intersection is just a zero vector. Right? This is actually the exact same reasoning as 3, just applied to any subset. Okay, and then finally, let's suppose that U is a subset of W. These are just any subsets of V. And let's suppose that V is in W perp. Okay, I'm trying to show that W perp is a subset of U perp. So it's enough to show that V is in U perp. Right? Then what this says is for every W in W, the inner product of V and W is 0. That's what it means to say that V is in W perp. But notice that U is a subset of W, which means that V is also going to be orthogonal to every vector in U. Because it's orthogonal to every vector, it's orthogonal to every vector in W, that means it's definitely orthogonal to every vector in U. So since now if U is in U, that means that U is in W, which means that the inner product of V and U is 0. This is true for every U in U, which means that also V is in U perp. And therefore, I've shown that every vector in here is also in here. So I've shown the inclusion that I wanted to. Okay. So those are some basic properties that just show you how to use the definition. Let me go back to this picture. It seems like we still have not yet proven all of the intuition that we get out of these geometric pictures. Right? Like somehow what these pictures tell me is that if you look at U and you look at U perp, it should sort of somehow cover the entire space V. Right? Like if you imagine now you take the picture in R4 and you take U to be a single line, it seems like the perp should be a 3-dimensional plane through the origin. Or somehow they're sort of playing off each other, so the bigger U gets, the smaller U perp gets. And basically it looks like, if you look at this picture, if you look at the vectors in U and the vectors in U perp, they should sort of span the whole space. And it turns out that the way to say this is to say that the vector space is going to be the direct sum of U and its orthogonal complement for any subspace U. Because writing as vector space as a direct sum right? So this should mean something like V is equal to U direct sum U perp. Because writing a direct sum like this says that you can break V up into two pieces, U and W, if you're writing as a direct sum like U and W, and those pieces intersect as small as possible, right? That's what we saw when we looked at direct products of two subspaces. It's a direct product if the intersection is 0, which is what's happening here. So that's the next result. So if U is a finite dimensional subspace, so I need it to be finite dimensional because I'm going to end up taking a basis of U and proving this. Then V is the direct sum of U and U perp. Okay, and just to remind you, this means every vector in V can be written in a unique way as a sum of something is a sum of a vector in U and a vector in U perp in a unique way. Or another way to say that is that V is the sum of these two things and the intersection is trivial. So this is if and only if V is the sum of U plus U perp and the intersection is trivial. This is by a theorem. And that's kind of good because we showed that the intersection of U and U perp is trivial. So we've done half of the work already, right? The proof. We already showed, this was just in the last result, that the intersection of U and U perp is trivial, actually for any subset U. So it suffices to show that V is equal to U plus U perp, that every vector in V can be written as a sum of something in U and plus something in U perp. Okay, and clearly, I mean, U and U perp are both subspaces of V, so definitely U plus U perp is a subspace of V. We just need to prove the reverse inclusion. We just need to show that every vector in V you can write as a sum. Okay, so suppose V is in V. What I want to do is I want to write V as the sum of something in U plus something in U perp. So I want to write it as a sum of something in U. So, I mean, the first term is going to be in U. So it would be nice to have a basis of U around. In fact, it'd be nice to have an orthonormal basis because I know I can get one. So let's choose an orthonormal basis of U. And now let's rewrite V in a clever way. How are we going to rewrite V? Well, what we can do is this is going to end up being essentially the projection of V onto U. But this thing is not yet equal to V because this is a vector in U and V does not need to be in U. But I can write it plus some other stuff. So let's write V minus the stuff that I added. Okay, so all I've done is I've taken V, I've added stuff, and I've subtracted off the same stuff. And let's call this vector U, because this thing is going to be in U. And let's just call the rest of this thing W. Right, so clearly U is in U because the E's were a basis of U. So what we want to show that W is in U perp. If you could do this, then you'd be done, because you've shown that every vector V can be written as as a sum of something in U plus something in U perp. So is W in U perp? Well, I need to check if it's orthogonal to every vector in U. But it's enough to check that it's orthogonal to every basis vector. So now note that if you take the inner product of W and say E1, what do you get? You get, this is what, this is W, and let's take the inner product with E1. Okay, but inner products are linear in the first slot, so I can break up this inner product. Oops. So the first thing I get, VE1 minus, also I can pull out scalars. So that's a scalar, and then I get the inner product of E1 with E1. Then I keep going, and I can pull out the scalar and get the inner product of EM with E1. There, I just use the linearity of the inner product in the first slot. And now what's nice? Well, E1 with E1, this is an orthonormal basis. This is just the scalar 1. And then all the rest of the inner products with EM and EM minus 1 and E1 and all the rest of them with E1 are 0 because it's an orthonormal basis. So this in the end just becomes the inner product of V with E1 minus itself, which is 0. Which means that this vector W is orthogonal to E1. But this exact argument works if you take any EI. Right? One term will be non-zero, but it'll cancel with the first term. So similarly, the W is orthogonal to EJ for all J, which means using the linearity, not quite using linearity, but this is equal to 0 for all U and U. What you do is you just write U as a, maybe I should use like U prime because I already used U. You just write U as a linear combination of the E's, and then you break up the sum over the inner product. And then you can pull out scalars up to complex conjugate, but they're all going to be 0 anyway, so the scalars won't matter. So this means that W is in fact in U perp. So every vector in V can be written as something in U plus something in U perp, and U and U perp intersect trivially. That means that V is the direct sum of U and U perp. Okay, so really the clever thing here was to figure out which vector in U you could find as a summand of V. But this expression for U that we've written down here, we've already written down expressions like this several times in this course, so it's not such a crazy thing to write down. As I sort of maybe said in passing, this is the projection of V onto U. It seems like it's a reasonable enough thing to write down. We also have a corollary of this results, which is, whoops, corollary of this result, which is, suppose V is finite dimensional and U is a subspace. Then the dimension of U perp is equal to the dimension of V minus the dimension of U. Okay, this is just because we proved that the dimension of a direct sum is the sum of the dimensions of the subspaces involved. This was a long time ago. So proof. We proved that as long as everything is finite dimensional, the dimension of U direct sum W is the dimension of U plus dimension of W. as long as U and W are finite dimensional. And so since we assume that V is finite dimensional, that means that every subspace is finite dimensional. So U and U both have finite dimension. And then we just prove that U plus U perp is equal to V, which means that their dimensions need to sum up to the dimension of V. So this is, I think now we're getting what our intuition said we should get from this geometric picture, that somehow V is, you can break up V into a subspace and its orthogonal complement, and therefore the dimensions need to add up to the correct thing. It's a thing that we noticed even when we're just drawing these pictures. Okay, another thing that I mentioned maybe is the following result. So suppose that U is a finite dimensional subspace now. Then if you take the orthogonal complement of the orthogonal complement, you get back to the subspace you started with. Okay, note that this word subspace is crucial here. If I said subset, this result would not be true. Right? If I said subset, then I could take a subset that wasn't a subspace. And then if you take its perp, you get a subspace. You take the perp again, it's still a subspace. So if you started with something that's not a subspace, you can't hope to get U back if you perp twice. But here I've said that U is a subspace, so this result seems reasonable enough. So let U be in U. Then, by definition, for every V that's in U perp, the inner product of V and U is 0. Which means that U is orthogonal to every vector in U perp. Which means that U is in the perp of U perp. Right? U is orthogonal to every vector in U perp, which means that U is in the orthogonal complement of U perp. So this means that U is a subset of U perp. Okay, and this is actually true here. I did not use that U was a subspace. Even if U is just a subset, it will still be a subset of U perp. For the other direction, somehow I'll have to use the fact that U is a subspace in some way. Okay, now suppose that V is in U perp, which is a subspace of V. Okay. Now, by the previous proof, since V is a vector in V, I can write it uniquely as the sum of something in U plus the something in U perp. And here I am using the fact that U is a subspace because that's what the previous proposition relied upon. So by the previous proposition, V is equal to U plus W, where U is in U and W is in U perp. Okay. But now V is in U perp. Okay, so then, what am I saying? Okay, V minus U equals W, and W is in U perp, right? That's what I'm trying to say. And since U is in U, this means that U is in U perp. That's what we just showed in the previous half of this proof. And also V is in U perp. that's what we're supposing at the start. So this means that v minus u is in u perp. Okay, therefore, this vector w, which is v minus u, is in u perp, and it's in u perp. Which means that w is in the intersection of, or v minus u, whatever you want to say, is in the intersection of a subspace and its perp. But the intersection of a subspace and its orthogonal complement is 0. So altogether, this says that since this vector lives in the intersection of something with its orthogonal complement, this implies that v minus u equals 0, which means that actually v equals u. Which means that I just assumed at the start that v was in u perp. And what I got was that v is equal to u, which is in u. And so this shows the opposite inclusion, which means that those two sets are equal. Okay. Now what we'll do is we're going to make more rigorous this notion that I've been talking about projections onto a subspace. So I've used it several times, and like we've even written the correct formulas. Like for example, in the Gram-Schmidt procedure, I told you, oh, what you're doing is you're subtracting off the projection onto the subspace spanned by the previous Gram-Schmidt vectors. But we didn't actually say what that meant, right? So, and earlier today, even at some point, yeah, in this proof, I said, yeah, this v, this is like the projection onto u. What is the idea of projection? Here's the picture. Right, the idea is you live in some vector space v, you have some subspace, some subspace u. What projection does is it takes any vector you want in v, and it spits out a vector in u. So if this is v, this is the projection of v onto u. Maybe I should make the u big. Somehow, what we want it to be is it should return the closest vector in the subspace to the vector we started with. Okay, maybe a two-dimensional picture is also good. So now, this is 2 dimensions. I don't have that much room to play with. You have some subspace u, like this, of v in 2 dimensions. You have some vector, whatever vector you want, some v like this. The projection should be the closest vector in u to v. This will be the projection. And like in this geometric context, closest means you'll have like right angles here. Right? So this is the picture that you should be thinking about. But we're sort of going to learn all about projections, how to compute projections, what properties they have. Throughout, you should be picturing these pictures. If I think about projection, I think about probably this 3-dimensional picture. That's why I drew it first. Okay. But I thought about trying to type these up in the notes, and it seems not that fun. If one of you wants to do it, learn some LaTeX, you can send me the code and I'll include it and I'll thank you in the notes. But okay, here's the definition. Let U be a finite dimensional subspace of V. What I want to do is I'm going to define projection onto U. The orthogonal projection of V onto U is the operator PU. This is an operator on V defined as follows. Okay, and how should it be defined? How should projection be defined? I want this to be the projection. I want this to be the projection. And this thing is going to be orthogonal to the new vector. So in other words, what I want to do is I want to write V as the sum of something in U plus something orthogonal to U, because that'll get me as close as possible to the vector. And then I want the projection to be the part that's in U. So that's how I'll define it. So for V and V, write V as U plus W with U in U and W in U perp. Then I'm going to define PU of V to be U. You write V as something in U plus something in the complement, and the projection is the part that's in U. Okay, and note that we proved that V is equal to the direct sum of U and U perp, which means that there's a unique way to do this. There's only one way to do it, and so this function is well defined. If there were more than one way to do it, then you wouldn't know what the projection of V would be, because it depends on how you write V as the sum of something in U plus something in U perp. But since it's a direct sum, there's only one way to do it. Therefore, I'm picking out a unique vector to be the projection of V onto U. Okay. So this is the picture. This is the definition. And hopefully you find the definition to be motivated by the picture. This is also the reason that we started talking about orthogonal complements, right? The reason we started talking about orthogonal complements was so that we could get this green vector here to be as small as possible, short as possible. The way to get that as short as possible is to be moving orthogonally to U. Okay, so now long results, properties of projection. So as always, we're going to let U be a finite dimensional subspace. And suppose that V is a vector in V. Then, so I'm going to write down 9 statements. So 1, first of all, the thing that we defined is actually a linear operator on V. I guess I probably stated here that it's the linear operator defined as follows, but we didn't justify that this actually was linear. So as defined, it doesn't necessarily seem like it's linear. It's not that obvious anyway. So it's a linear operator. Okay, 2. If I project a vector that's already in U, what do you think you should get? If you project a vector that's already in U onto U, what it should return is it should just return that vector back, right? So P of U should equal U for all U and U. Okay, what if you project a vector that's in the perp? Again, let's look back at this picture. So if you projected a vector that was in the perp, so here's like U perp, right? If you projected a vector that's in the perp down to U, what you expect to get is the 0 vector. So this is equal to 0 for all W in the orthogonal complement. 4, the range of this linear transformation, that should just be all of U. right? What can you get out of projection onto vectors in U? You should be able to get everything in U. The null space of this thing, right? Which vectors get projected to 0? Well, based on this increasingly complicated picture, seems like maybe it should be the orthogonal complement of U, which is exactly correct. 6. If you take V and you subtract off its projection, what do you get? Maybe I should draw some more pictures here. That one's getting kind of cluttered. So let me just draw another picture again. So if you take V and then this thing is going to be PU of V. If you subtract V minus PU of V, what are you doing? It's like you're taking, maybe I'll draw this one in green. It's like you're taking V and you're subtracting off this bit. So the new vector you're getting is this vector. And it seems reasonable to me that that thing should be in the orthogonal complement of U. So if you take V and you subtract off its orthogonal projection, this thing is in the orthogonal complement of U. 7, what happens if you project twice? Well, if I take a vector and I project it to U, and then I project it to U again, the result, that should be the same thing as just projecting once. If you project again, nothing new should happen. So projection twice should be the same thing as projection once. Okay, 8 is maybe something that we could also try to think about in the picture. If I take the norm of a vector after I project it. So I take a vector, I project, and I look at the length, right? The length of this vector versus the length of this vector. Well, it seems like the new vector is shorter. That's true. This is less than or equal to the norm that you started with. And then finally, if E1 through EM is an orthonormal basis of U, then PU of V is just the following linear combination. The scalars are given by inner product of V with the corresponding basis vector. Okay, so all these times that I've said projection onto a subspace kind of vaguely, this was exactly the linear combination that we were taking. Right, so for example, in this earlier proof, I said, oh, this is like this blue underlined part. Oh, that's like projection onto U. That's exactly what it was. You chose an orthonormal basis of U and you projected V onto U. So maybe you should go back to this theorem and think about what the picture of U and W is and why it sort of makes sense that that's how you could break V up into something in U plus something in U perp. Okay, so long result, we should prove, I guess we should prove all of it. Some of it will be kind of quick, some of it less so. But I imagine we can do it in the next less than 15 minutes, which is how much time we have left. I have left. Okay, so first, let's prove it's linear. Okay, so you need to show that it's additive and homogeneous. As always, let me do half of it. So suppose that V1 and V2 are both in V. Okay, now let's write V1 equals U1 plus W1 and V2 equals U2 plus W2, where the UIs are in U and the WIs are in U perp. And there's a unique way to do this because V is the direct sum of U and its complement. Okay. So why did I do this? I did this because by definition, PU of V1 is equal to U1 and PU of V2 is equal to U2. Now, I want to know PU of V1 plus V2. right? So note that v1 plus v2 is equal to u1 plus u2 plus w1 plus w2. And u1 plus u2 is in U because U is a subspace. W1 plus W2 is in U perp because U perp is a subspace. So PU of V1 plus V2 is exactly the U part of this. So PU of V1 plus V2 is defined to be U1 plus U2. Which means that this is equal to this plus this, which is exactly what you need to show that a map is additive. So PU is additive, and you should check homogeneity. Okay. Now for the rest, I'll at least do all the ones that I can at the time. I mean, they're all proved in the notes. So 2, I need to show that projection of something in U just returns the vector that you want, but this is basically a one-liner by definition. So let U be in U, then U is equal to U plus 0, right? With U in U and 0 in U perp. And this is the only way to write U as the sum of something in U plus something in U perp. And so by definition, PU of U is equal to the U part, which is U. Okay. 3 was we were trying to show that if you take something in the complement and project, you get 0. So let W be in U perp. Then what? Then W is equal to 0 plus W with 0 in U and W in U perp. So by definition, PU of W is the U part, which is 0. Right, so again, these kinds of properties seemed reasonable based on our geometric intuition, but here we're using the definition of projection. So I mean, you could prove this without understanding any geometry. But it's always powerful to be able to picture things and what they really mean, right? So you shouldn't struggle to remember these results because you have a picture of what projection looks like. Oh, if I take a vector in the plane and project onto the plane, then that vector is going to go to itself. If I take something in the normal vector to the plane and project it, I should get 0. Okay, for the range. So since if V equals U plus W with U and U and W and U perp, PU of V equals U, this is how we defined it. It's very clear that the range of PU is going to be a subset of U, because by definition, what it spits out is a vector in U. Right, so this, basically by definition, the range of PU is definitely going to be a subset of U. The way that we defined it is to write it as something in U plus something in W and return the U part of it. So everything that spits out will be in U. Okay, conversely, I need to show that U is a subset of the range. In other words, I need to show that you can get every vector in U by projecting. But if I want to get some vector, how do I get it out of the projection? I just plug it in, and then the projection leaves it unchanged. So conversely, if U is in U, then if you project onto U, by part 2, this is just U. So U is in the range of PU. And these two things together show that the range of PU is actually all of U. Okay, cool. 5, what was I supposed to show? The null space is the orthogonal complement. Okay, well, part 3 shows that the orthogonal complement is a subset of the null space. Everything in the orthogonal complement goes to 0. So by part 3, the orthogonal complement is a subset of the null space. So conversely, suppose V is in the null space, but since PU of V equals 0, what does this mean? This meant that you could write V as 0 plus something in U perp. Where where 0 is in U and W is in U perp. But V is just W, right? So this means that V is in U perp, which shows the opposite inclusion. The null space is a subset of the complement of U. Okay, really roaring along here. Number 6, what we're supposed to prove. That if you take V and you subtract off its orthogonal projection, you get something in the orthogonal complement. You should be able to do that. So 6. If I can write 6. So again, let's write V equals U plus W with U in U and W in U perp. Okay, then the thing I'm interested in is V minus PU of V. But V is equal to U plus W, and PU of V is equal to U, just the U part of that. So this is W, which is in U perp by definition. All right, so if you subtract off a projection, you get something in the complement. Okay, 7. Sorry, what we're trying to prove? We're trying to prove that if you do the projection twice, it's like doing the projection once, right? Again, let V and V, and write, I've written this 100 times now, V is equal to U plus W, where U is in U and W is in U perp. Then let's project twice. Well, this is the projection of the projection. But the projection once would return U, which is just the same thing as U, because U is in U. But U is also what you would get if you projected V just once. So if you project twice and project once, you got the same result. That is true for every vector V and V, which shows that those two linear maps are the same. Whew, okay, almost done. 8. The projection is shorter than the original vector. The projection has a smaller norm. So 8, again, right? V equals U plus W with U and W and U perp. Okay, then let's look at the norm squared of this vector. Well, the projection is just U. It's the norm of U. Okay, but this is less than or equal to if I add the norm of U to it. I've only made the thing bigger. And now these are orthogonal, remember? So here we can use the Pythagorean theorem. But this is just the norm of U plus W squared, which is this U plus W is just V. Right, so here's a good place where we see the power of the Pythagorean theorem. Okay, and then the last thing that we want to prove, number 9, was that this is the formula for the projection. This is kind of an important thing. But actually, we've already seen that it's the formula for the projection back in the proof of this thing. This proof, starting here, applies to any vector v and v. You can always write v like this sum, the sum of this plus the sum of this. And then we showed that this vector is in U and this part is in the complement, which means that if you project, you should take the U part. So this must be the projection of V onto U. So actually this proof shows that the first underlined part is the projection onto the subspace U. So 9 follows by an earlier proof. Since you can always write V like this, plus V minus this. And this part is in U. Maybe I should say it's in U. And this part is in U perp. We checked that. Which means that this thing is equal to the projection of V onto U. Okay. So, I mean, I guess that last part, that was a 9-part thing, although these properties seem very reasonable once you have a geometric picture. The main takeaway from today, 1, the definition of the orthogonal complement and its basic properties. And then this is maybe the more important definition, the definition of projecting onto a subspace. And the thing to, if you're going to memorize something, you should memorize this formula of the projection onto a subspace. And remember that this relies on an orthonormal basis. Okay, so next time we'll discuss some applications of orthogonal projection. There's like many actual real life applications. So this is the section of 6C called minimization problems. So that'll be Wednesday. And then maybe even on Wednesday, we'll start moseying on into chapter 7. All right.